So it's my pleasure to introduce our next speaker this afternoon session, which is Nelson Martins-Ferreira from Politécnico de Leiria.
Thank you very much. By the way, it's Leiria. How to pronounce it? It has to do with double R's. As in Ferreira, with the double R squared. That's it. So, it is a great pleasure for me to be here. Thank you very much to the organizers for this wonderful conference, which is just the start, but I'm sure it will be all very good until the end. It is a very good opportunity to know new people, to exchange ideas, to absorb ideas from other researchers. And actually, this is how I feel it. We spend a lot of time in our caverns, alone, working, thinking, sometimes not exactly alone, with collaborators, but very few, 2 or 3. And in this occasion, we have the opportunity to come here and to show our ideas and to listen to ideas from others. So thank you very much for organizing this conference. Okay, so this is joint work with Manuel Sobral, and essentially I will be talking about a paper which has recently been published. I will just give the reference in the end. So most of my talk, sorry to say, it's advertising the paper, and there is only one little new thing which is not in the paper, and I will make note of it. So this is about, this is to report a work which we have been doing in the study of monomorphisms in the category of monoids. So unlike in the Maltsev context, so for instance in groups, where every reflexive relation is automatically an equivalence relation, so there is nothing in between. In the category of monoids, there is a rich variety of notions that can be considered normal monomorphisms. Example, we will have the positive cones, so the zero classes of preorders. We also have clots, which are the zero classes of reflexive relations, nothing more than just reflexive relations. And of course, we have the normal submonoids, normal subobjects, we call it, as the zero classes of congruences. And it shows that there is a rich variety of such notions, so that's why I will try to go through it. And this suggests a nice way of, so by looking at the example, in the concrete example in the category of monoids, we could arrive to a notion which somehow has the flavor of categorical concept and can be worked out in any category. But of course, the motivation and the example came from the particular study of the case of monoids. By the way, so this has to do with normalization and denormalization. So for a relation, let us say, an internal relation in thinking in the category of monoids, taking its normalization is taking its zero class, and the converse is denormalization, so that from a zero class try to reconstruct the relation which has given rise to that zero class. And since this has many applications in computer science, so computer scientists, they very much use the category of monoids. So we try to look at what is going on in the context of data science and so on. And this problem is also a big issue there. The question is to denormalize or not to denormalize. In a sense that, so this is now the intuition so that you can have, it's from the computer science in the sense of databases, so relational databases, in which you can have the the minimal information of your database, like just one copy of each item in the database. So this is the minimum. And then they say that the database is normalized. Okay? There is no redundancy in the data. On the other hand, you can have the same database with extra bits of information which are redundant but are useful for queries. So if you want to find something in your database, it's sometimes useful if you have some shortcuts that will point to that query in a shorter time. But there is redundancy to that. And so they call this, the database has been denormalized. Okay? And I think this is a good intuition for the categorical notion, because we are not talking about databases, but we talk about relations, internal relations, and we will be interested in either taking its zero class or from zero class to get the normalized relation that gave place to it. So let me start. Okay, so first of all, let me give some little motivation. So let us consider a graph over B. Okay, so an internal graph in some category, but you can think of category of monoids. So the reason I am kind of mixing in here some notations, I'm using D and C as notation for graph, domain and codomain, but I am using R in the sense that very soon we will be considered just relations, so that D and C will be jointly monic and we'll see it as a relation. But before, I would like to give the idea that it's better to think of arrows in a graph rather than elements being in relation or not. It's more visual to think of that. Now, suppose we have a morphism into B, let me call it H, and so we still have the graph here. So in order to not to lose which one is first projection when we think of relations and which one is second projection, because when we think of relations we say R1 and R2 or R0 and R1, there is a lot of possible notations. So I consistently use the notion that we have when we write the arrows, it's from left to right, so there is a notion of top and bottom. And so whenever the diagram is written vertically, it should be read from in this direction. So this is always domain, this is always codomain. Okay? There is direction, there is a sense of direction here, which will not create confusion to say which morphism is domain and which morphism is codomain. Think of codomain as first projection, think of domain as second projection in the sense of a relation. Alright, so the thing is, can we detect whether the image of this morphism H is a connected component of our graph? So, say, given two elements in X, if we have the images like this, can we find something here? Okay, and so that we will see it as a connected component. So I'll just this is still for motivation, and I'll just do a little example which will be used later on. I will come back to it later. So for the moment, let me just observe very simply that if our graph is symmetric, so there exists a morphism phi such that domain of phi is codomain and codomain of phi is domain. So it just inverts the arrows. And if our graph is also transitive, so we have a morphism such that domain of tau is domain of second projection, codomain of tau is codomain of first projection, so these projections used for the public. Then, if we have also a chosen element in B, let me call it 0 because we will continue to use intuition from the pointed context, but it can be any element in B. So if we have such, so let me put 0 here, then it is clear that we can always have such a thing here because, well, okay, I'm going ahead. It is clear as soon as we, it's there. So as soon as we assume that somehow we can see the morphisms, the elements here, as living there. Under some condition. And what is the condition? So if we can, somehow can realize the elements as arrows, let us say, so let me call this, there is a morphism Q here, and each element in X can be seen as an arrow starting from 0 and landing in H of X1. So we will have an arrow here, we'll have an arrow here, and now the usual tree. So invert and compose. And so in this case, we see that the component is connected. So what does it suggest? So it suggests that in the case, so let me now say when the pair DC is jointly monic. So we are now talking about relations, no longer graphs. So when this is a relation, then what we asked about this morphism K was simply that, and there exists K from X to R, such that dk is 0 and ck is H. If we have this, then, assuming symmetry and transitivity, we will fulfill the component. So we say that, in this case, we say that R contains H. So this is just notation. Okay? Moreover, if in addition K happens to be the kernel of domain, then we see that H is the 0 class of the relation. Okay? So we say that H is a 0 class. Okay. H is a 0 class of R when K is kernel of D. Okay, this is what is written there. Okay, so far this was for motivation. So motivation is now ended, and we now move to something else. So it has been criticized the following definition: a monomorphism is said to be normal if it is the 0 class of an equivalence relation. In particular, Medjere has a beautiful paper studying the notion of normality in the context of regular Maltsev varieties and categories. And it's an observation there, and I happen to agree with it. This is not so nice as a definition because it involves an existential quantifier there. So what does it mean? It is normal to it is the 0 class of an equivalence. Where is the equivalence? What equivalence? If I want to check, do I have to check to all possible relations, or there is something which I can more conveniently check? Moreover, in my paper with Manuela Sobral, so I will refer to it as this, it's from 2023, there it is very clear, as I was saying, that we not only have normal in the sense of a zero class of an equivalence relation, but of course you can, if you say zero class of any relation, you get a monomorphism. If you say zero class of a reflexive relation, this is what has been called before a clause. If we take the zero class of a preorder, it is called a positive cone, it was mentioned before. And of course, the equivalence relations is when we get the normal submonoid, which is the same as the kernel, but in the case where equivalence relations are not necessarily equivalence relations are not necessarily effective, the kernel pair of some homomorphism, there is still the difference between normal monomorphism in the sense of a zero class of an equivalence relation and the kernel. Okay, there is still the disagreement in that sense. Okay, so let me just give you a taste of what results can you find in the paper. So that H from X to B could be a monomorphism. So in this intuition, in the category of monoids, it is a positive cone. So it is a zero class of a preorder if and only if this condition, well, these are the equivalent conditions. So it is a positive cone, it's the same as there exists an internal preorder which contains H as a zero class in this sense. H is the zero class of the smallest preorder containing H. H is the zero class of its syntactical preorder. It is something that comes from computer science. I will not enter into much details here, but the zero class of the syntactical relation is the second condition here on the right. Okay, so you see the different flavors. So the top condition on the right is obtained by generating the smallest preorder containing the image of H. But if we generate directly the syntactical preorder, which I don't think if someone is interested, I can give more details, but I don't think it is a point in going in that direction. But it comes from computer science. It's something which has been studied. It has been introduced by Allenberg in the 60s in his volume on machines and automata and etc. So the syntactical monoid is a little bit previous to that, but it's the first book where you can find the reference to the syntactical. Actually, they study the syntactical congruence, then the syntactical preorder is a slight variation, and that's it. Don't want to take too much time, but in the end, if I have time in the end, I can give more details. So let's continue. Perhaps just one little note extra that so what is the advantages and disadvantages of the two types of conditions? So in this one it seems simpler, so it seems that this one is much more complicated, but this one has the advantage of if you have some sequences of elements in B, sequences of elements in X, so double indexed sequences, if something sums up to 0 and some combinations happen, then in the end we conclude that certain formula belongs to X. Whereas here it seems simpler, but the trade-off is that we don't have equations in this part. So this is like if something is in X, then something else is in X. Okay? But for computer purposes, this is a good notion. But from algebraic point of view, the other description is more convenient. All right, let's continue. Yeah, this would be the place where I would advertise and I would give more details on this syntactical preorder and so on. And for those who would be not interested, you could appreciate this beautiful art, which I'm sure you could spot where it is located. But so I think I will, in the end, if I have time, I will give a little bit more details, but for the moment, I will just continue. And all the details are in the paper, so if anyone is interested, I think it's sufficient to refer to the paper. All right, so what else do we have here? Aha, the connection with the normality in the sense of good. So the definition is here on the right. It has been referred in this during the one talk in this morning. And but this definition, although it is very good, it has many classifying properties. It has been used for 20 years or more than 20 years now, because originally it was in 2000 the original paper by Boone. So this definition in particular, I refer to the paper with Boone and Grant from 2002, but it's the same as the original one introduced by Boone in 2000. So it has been used, but somehow it has not been clear what kind of zero class. So how does it behave with this zero class and normalization and denormalization? So it is a natural question, since we investigated this all notions in monoids, to ask the following question: can we find in this sense, so in the sense of, can we find a characterization of Boone normal in this, using this language, okay, which is different from the definition? And so, perhaps not surprisingly, the answer is precisely transitivity and symmetry. So we observe. Oh, I think I went ahead. So this was spoiler alert. So there were some little observations I would like to do, but then since I went ahead, let me go and then come back. So there is this result. So a morphism in the sense of a morphism H is normal in the sense of Boole, if and only if it is the zero class of a symmetric and transitive relation, provided we make the following slight adjustment. And this is now what I have to explain with slight adjustment. So the definition, and for that, Metzger in 2017 suggested that a morphism, so in this new notation, but it is the same as from this paper, a morphism H is said to be Boole normal when there exists an equivalence relation, R, such that H is normal to R in the sense of Boole, okay, in the sense of this definition. Now, what we observe is that the relation is, so it's required to be an equivalence relation, but in the definition, the fact that the relation is an equivalence relation is never used. So this definition actually works for every relation. So we can define this structure. Essentially, the structure is this map H bar. So there must exist this morphism H bar satisfying to these two conditions. And this can be asked for any relation. So what I was saying is, if we slightly modify this definition, and instead of saying that there exists an equivalence relation, we say that there exists a symmetric and transitive relation such that H is normal to it in the sense of Boole, then we can prove this result. That in that sense, a morphism, which necessarily will be a monomorphism, is normal in the sense of Boole, if and only if it is the zero class of a symmetric and transitive relation. And the essential point in the proof is here. We need to present this morphism H bar, which is precisely given by this formula that I mentioned before. So this is H bar of x1, x2, which is required in the definition of normal in the sense of full. Okay, going a little bit ahead. So just to recall, so we have different, for every type of relation, we can speak of normal with respect to it. So if we take only relations and normal to it, we get monomorphisms. If we take reflexive relations, we get plots. Reflexive and transitive or preorders, we get positive cones. So now we can add this new. So if we take symmetric and transitive, we get normal in the sense of Boole with this change of replacing equivalence relation by symmetric and transitive in the definition of the notion of Boole. And if we take equivalence relations, we get normal suboptimal. So, natural question is, what classes are suitable to define this normality in this sense? And the answer is quite categorical, but also quite natural. We should ask that the normalization functor has a left adjoint, which denormalizes the morphism, and associates to each morphism the smallest relation containing it. And so again from the paper, this is where we observe that then there is all these equivalences between a morphism is normal if it is the normalization of this, it's the normalization, and etc., etc., etc. So I think it is time to stop. Referring to the paper, and the other references are here. Thank you very much. This is all.